So previous week we studied a particular matrix called the omission matrix. When A dagger is A, it is called omission matrix. And dagger is actually transpose plus complex conjugate. Then I stated the theorem that set of real numbers alpha 1, alpha n, and on orthonormal basis vectors which I used EI. Oh, I think I used a lambda, right? Lambda 1, lambda 2, lambda n, such that is identity matrix, and alpha I, lambda I, and I showed a few examples, right? And orthonormal means, and also lambda I, lambda j is delta ij. And I still left a blank that, so what is those numbers and what are those numeral vectors, right? So how can you, so this is, it is a name, it's called the Spectral Theorem. So I just stated without proving the theorem, and actually I showed few cases, right, few examples that essentially this statement is true. I wouldn't say it's a complete mathematical proof, but I think at this stage it might be just good enough. So under which conditions that we can actually find those numbers, set of numbers, and those set of orthonormal vectors would be very interesting, right? So the question is, how do we find right for spectral theorem? or maybe that expression would be for A to satisfy the spectral theorem. So that would be the question. I mean, okay, so and we learned that using spectral theorem we can do many convenient things like multiplying the matrix many times, right? So we have actually considered the case of multiplying some particular matrix a million times or 100 million times. In actual time, if you just actually multiply, even for 2 by 2 matrix, maybe a million times, it will take a lot of time. Right? But if you can apply the spectral theorem, then you can actually calculate those the matrix multiplication in maybe 2 seconds. So actually, spectral theorem is a very powerful tool, but still we have the question: how do we find those set of real numbers and those orthonormal vectors? The answer is solve the eigenvalue problem. So A lambda is lambda lambda. So say A is a n by n matrix, omission matrix. Lambda is called eigenvector, and this lambda is called eigenvalue. So actually solving this eigenvalue problem is also quite straightforward. So I'll give you some more time to copy. Oh, okay. So starting with this particular problem, so this is basically the following. You have some cat vector. By now you have to be familiar with this notation. This is cat vector, this is a column vector, right? So if you multiply n by n square matrix to the vector, then the result is the same vector multiplied by some constant. So that's the nature of eigenvalue problem. And how do we solve this? You need to find the lambda and the vector lambda. So you can actually move this way, a minus lambda I, lambda is 0. So let's call this a prime. So if A prime is an inverse, what happens? Simple. When A prime is an inverse, this lambda vector is very 0, right? Then it has to be 0, right? So if you want to get some meaningful result, the only condition is A prime should not have the inverse, right? So this is so trivial. So we have only one vector, and what we need is a set of orthonormal vectors. So that so A should not have an inverse. remember, go back to the definition of inverse matrix, A prime. What is the principal condition that the inverse matrix exists? Determinant A prime should not be 0, right? So, opposite way, if the inverse should not, then condition should be determinant A has to be 0, right? Not here, not have an inverse. And this condition is actually determinant A prime, determinant A minus lambda I should be 0. Then we can get the set of polynomial equation for lambda. So let's consider some example. I will let you review the previous statement and okay, so obviously A is summation, right? So A dagger is A, this is summation. So A prime is A minus lambda I minus lambda 1, 1 minus lambda, right? So determinant A minus lambda I is lambda square minus 1 equal to 0. So lambda is plus 1, lambda is minus 1. Remember that I somehow introduce alpha 1 is 1, alpha 2 is minus 1, right? So let's try to find the orthonormal vectors. So case number 1, when lambda equal to plus 1, then A, and we say lambda is simply x, y. And, okay, I'm going to put lambda 1. Lambda 1 is plus 1. So A lambda 1 is plus 1 lambda 1, right? Or 0, 1, 1, 0, xy is equal to xy, so which means y equal to x and x equal to y. So you can have arbitrary solutions. So what you can do is actually set x equal to 1, then lambda 1 is simply 1, 1. But the condition of the orthonormal vector is I can use lambda 1 is what? 1, 1, 1, 1 is 2, right? But the orthonormal vector means when you have an inner product with itself, it should be 1. So we can actually define from this, we set lambda 1 with tilde as square root to 2 over 1, 1. Something familiar from previous class? And let's consider case 2. When lambda 2 is minus 1, then we can do the same thing. Set lambda 2 as xy, then a lambda 2 is 0, 1, 1, 0. xy is simply, if we multiply by this and this, it gives y and x is minus lambda 2, which is minus xy. So y is minus x. So we can set lambda 2 is 1 minus 1. And if we take the inner product with lambda 2, which is 1 minus 1, 1 minus 1 is again 2. So we define normalized eigenvector lambda 2. One minus 1. Let me see. So we have lambda 1 is equal to plus 1, lambda 2 is minus 1, and normalized eigenvectors 1, 1, lambda 2, 1 minus 1, and we need to check that they are orthonormal. So lambda 1, lambda 2 tilde, 1 half, 1, 1, 1 minus 1 is 0, right? So they are orthonormal. And I don't have to repeat because I already have shown that this satisfies the set of numbers and vectors satisfies spectral theorem, right? So previously, and and they use for the spectral theorem. So I'm not going to repeat it again. You can check in example 2. So you can go back to your previous note. Then this lambda 1 and lambda 2 actually plus 1, minus 1, and this the vector with the tilde can be used to show the spectral theorem. I'm not going to repeat it. Another one is a bit more this is complex. So Hermitian transpose 0 I minus I 0. So A 0 minus I 0, A 0, there goes A. So this matrix is also Hermitian. So A is Hermitian. So far we have been calculating determinant only for the real matrix, and now we have a complex case to see what happens. So A determinant A minus lambda I is actually minus lambda minus I minus lambda. So this is lambda square minus I, right? So this is actually 1. So lambda square minus 1 is equal to 0. So lambda is plus 1 minus 1. So again, remember the expansion coefficient for previous classes. You can go back. Was plus 1 minus 1, right? And we normalize that vectors as a square root of 2, 1i, or minus 1i, right? So let's check. So consider. So lambda 1 is plus 1. A, and so we can check lambda as xy. A lambda 1, 0 minus I 0. Xy is actually minus IY, IX is XY. So they are the same result, so Y is IX. So from this we can set arbitrarily lambda 2 as 1i. And we need to normalize it. So 1 minus I, 1i is again 2. So square root of 2, 1i. So this is normalized eigenvector. So normalized means when you take the inner product with itself, it becomes 1. And when lambda is -1, you just need to make a copy. Am I going a little too fast? When case number 2, when lambda 2 is -1, so we can set, again, lambda 2 is any value, xy. So a lambda 2 vector is 0 minus I, 0, xy is minus iy, ix is minus xy, right? So this confirm this, y is minus ix. So we can actually set lambda 2 as 1 minus I, but it's not normalized vector. So lambda 2, 1I, 1 minus I is 1 plus 1 is equal to 2. So from this, we can normalize this vector as square root of 2, 1 minus I. So we have lambda 1 is plus 1. Lambda 1 vector is square root of 2, 1I. Lambda 2 is minus 1, lambda 2, square root of 2, 1 minus I. And familiar? But so actually I have shown they satisfies the Spectral Theorem, and still most likely you don't remember for last week's class, right? Most of you. 1 week is too long time to remember. So maybe for this particular problem, maybe I can do it again because the eigenvector contains the imaginary number, so we can do something. Still there's some time. Time to copy. So only thing is you need to calculate out the product. So lambda 1 tilde is a square root of 2, 1i. Lambda 1 is 1. Lambda 2 is minus 1. Lambda 2 tilde, 1 minus 1. So we need to calculate this outer product first. So this is 1/2. We have 1i. And what is the bra vector? You take a transpose and complex conjugate 1 minus I, right? So we have 1/2, 1 minus I, and 1. Lambda 2 is again 1/2. You have 1 minus I, 1I, because when you make a bra vector from cat vector, you take a transpose and take a complex conjugate. So it becomes 1/2, 1I, minus I, 1. So first checking point is you add lambda 1 tilde plus lambda 2 tilde lambda 2 tilde. That is 1/2 1 minus I 1 plus 1/2 1 I minus I 1. What do we have? One plus 1 is 2, divided by 2 is 1, right? Minus I plus I is 0. I plus minus I is 0. 1 plus 1 is 2, divided by 2 is 1. So this is basically 1, 0, 0, 1, which is I. On the other hand, the weighted sum, plus 1 lambda 1 minus lambda 2 is 1/2 1 minus I 1 minus 1/2 1 I minus I 1. So 1 minus 1 is 0. Minus I is 2I divided by 2 is minus I. I minus plus I is 2I divided by 2 is I. 1 minus 1 is 0. So it becomes 0 minus I 0 is A. So we obtain Spectral Theorem there. Right. So for 2 by 2, we can see that the spectral theorem is true, and then you can obtain a set of real numbers and a set of normalized orthonormal vectors by solving eigenvalue problems. Right? So actually, those set of real numbers and set of orthonormal vectors turns out to be eigenvalues and normalized eigenvectors over eigenvalue problem for Hermitian matrix A. So we know that that is true for 2 by 2, and mathematicians would be interested in just proving for n by n. But we are engineers, so for practical case, let's see. Actually, this relation holds for 3 by 3, and then after that, you should have a faith. So believe me, it's like math is in a way more like a religion. So you have to have a faith. So you should believe the spectral theorem is true. But before you believe that, I'm going to show one more for 3 by 3. That will be a bit challenging and also very exciting because 3 by 3 eigenvalue problem can be a topic for next quiz and next spectral theorem problems. And so I'm going to let's consider some simple Hermitian case. Okay, maybe I 1 1 0 1 0 1 0 1 1. So if you take this is a real case, real matrix. So the dagger adjoining to a dagger means just transpose. And you can see that when you take a transpose, it is the same as A, right? So A dagger is actually A transpose is same, right? 1 1 0 1 0 1 0 1 1. It's A. So this is Hermitian. So first thing we need to do is calculate, solve the eigenvalue problem first. So determine A minus lambda I is 1 minus lambda 1 0 1 minus lambda 1 0 1 1 minus lambda. So 3 by 3 determinant we need to expand over minor, right? So let's try to use this first row. So that is 1 minus lambda. Then you delete the first row, first column, you have minus lambda, 1, 1, 1 minus lambda. And second element is 1, but that's 1, 2, so you have minus sign. So it becomes minus. You delete the first row, second column, so we have 1, 1, 0, 1 minus lambda. 1 minus lambda, minus lambda, 1 minus lambda, minus 1, minus 1 minus lambda. So it can be factored with 1 minus lambda. And minus becomes lambda square minus lambda minus 1 minus 1 1 minus lambda square minus lambda minus 2. And this is very easy to factor. We have done that in middle school. So 1 minus lambda plus 1, lambda minus 2, right? So we have 3 eigenvalues. Lambda is 1, minus 1, 2. So it is interesting to note that somehow you can see the whole thing here. Screen is what happens. Why is it that? You can see 1 minus 1, 2, and this one you can see only 1, right? Is it something wrong with the screen, or the projector is not perfectly aligned? I think probably you have to let Doyeol. Right. I think the projector is not aligned well. So 1 minus 1, 2. So maybe we can arrange it in the ascending order. So say minus 1, 1, 2, right? Can I move on? Or it's going to take a little while, so maybe you can take a break. Continue. Right? Second quiz, April 10. It's going to be a simple 1-hour quiz, so 11 to 12. a.m. And then there will be a class, and if the attendance rate is very low, then you might have a surprise quiz. 시험은 11시 12시까지고 끝나고 수업하는데 만약에 출석률이 아주 저조하면은 깜짝 퀴즈 볼 수도 있어요. And there will be a class after that. So let's go back to A, 1, 1, 0, 1, 0, 1. 0, 1, 1. And we have three different eigenvalues. Lambda is minus 1, 1, 2. So start with the lambda 1, minus 1. Then let's say x, y, z. Then a lambda 1 is 1, 1, 0, 1, 0, 1, 0, 1, 1. X, y, z is x plus y, x plus z, y plus z is minus over x, y, z, right? So x plus y is minus x plus z is y, y plus z is minus z. So y is minus 2x. And y is minus 2z. So we can say that x equal to z, right? So tentatively, we can set lambda 1 as 1 minus 2, 1. But we need to normalize, right? Need to normalize. So lambda 1 is 1 minus 2, 1. 1 minus 2, 1 is how? 6, right? 6. So we can write down normalized eigenvector. Square root of 6, 1, minus 2, 1. So form of eigenvector means actually we have a position that our life is not going to be easy. So can I move on? Lambda 2 is 1. The right thing, x plus y. Right? So we can say lambda 2 as again x, y, z. So ax, a lambda 2, 1, 1, 0, 1, 0, 1, 0, 1, 1. X, y, z is x plus y, x plus z. Let me see. I think I was. And y plus z is simply x, y, z. X, y, z. So that means x plus y is x. Y plus z is z. So this means y is equal to 0, right? And x plus z is 0, so z is minus x. So we can tentatively set lambda 2, 1, 0, minus 1. So normalize lambda 2 means lambda 2, 1, 0, minus 1. 1, 0, minus 1 is 2, right? So the normalized eigenvector is square root of 2 1, 0, minus 1. Right? X plus z is y is equal to 0. So one more. So last is lambda is equal to 2. Can I move on to the next page? Right. So lambda 3 is 2. So set lambda, vector lambda 3, x, y, z. A lambda 3, 1, 1, 0, 1, 0, 1, 0, 1, 1, x, y, z is x plus y, x plus z, y plus z is 2y of x, y, z, right? So x plus y is 2x, x plus z is 2y, y plus z is 2z, y equal to x, y equal to z, right? So also x equal to z. So lambda 3, we can say 1, 1, 1, but we need to normalize it. Lambda 3, 1, 1, 1, 1, 1, 1 is 3. So normalized eigenvector is lambda 3 is square root of 3, 1, 1, 1. So we need to check whether these eigenvalues and eigenvectors shows a spectral theorem, right? So let's summarize the result so far. See, so lambda 1 is minus 1, and normalized eigenvectors square root of 6, 1, minus 2, 1. Lambda 2 is 1, lambda 2 is 1, 0, percent minus. Lambda 3 is 2. Normalized eigenvector is square root of 3, 1, 1, 1. So the first thing we need to do is next step is we need to show if orthonormal vectors, right? So we need to check that first, if they are the orthonormal vectors. So lambda 1, lambda 2. Lambda 1, square root of 6. And lambda 2 is a square root of 2. 1 minus 2, 1, 1, 0, minus 1. Obviously, 0, right? Lambda 1, lambda 3. Square root of 6, square root of 3. 1 minus 2, 1. 1, 1, 1. Is okay? 0, right? Lambda 2, lambda 3. Square root of 2, square root of 3. 1, 0, minus 1. 1, 1, 1. Okay? 0. So we have seen that at least those three eigenvectors, normalized eigenvectors, are orthonormal set. So we just found out that. Actually, that's also properties of Hermitian matrix. So if you see the eigenvectors and eigenvalues of Hermitian matrix, eigenvalues are real, and normalized eigenvectors form a orthonormal set. That's the two basic properties of a Hermitian matrix. And we just have checked that. And now go back to the spectral theorem if they really satisfies it. Can I move on to the next page still with copy? So, lambda 1, lambda, what am I doing? Lambda 1 is minus 1, so normalized eigenvectors are square root of 6, 1 minus 2, 1, lambda 2 is 1, normalized eigenvectors are square root of 2, 1, 0, minus 1, and lambda 2 is 2, 3 is 2, square root of 3, 1, 1, 1. So let's calculate this. One over 6, 1 minus 2, 1, 1 minus 2, 1, plus 1 half, 1, 0, minus 1, 1, 0, minus 1, and 3, 1, 1, 1. So 1, 6, 1, 2, 1, 2, this is minus 2, 4, minus 2, 1, minus 2, 1, right? 1 half, 1, oh, minus 1, 0, 0, 0, minus 1, 0, 1, plus 1, 3, 1, 1, 1, 1, 1, 1, 1, 1, 1. Maybe I should just use a small characters. So 1 over 6 plus 1 half plus 1/3. What do you have? 1, right? Minus 2 over 6 plus 1 over 3 is equal to 0, right? 1 over 6 plus minus 1 over 2 plus 1 over 3. What do you get? Zero, right? Oops. So 6 over, so this is actually, you can check, 6 over 1 minus 1 half plus 1 3. 6 over 1 minus 3 plus 2 is 0, right? So this is actually 0. And second row, minus 2 over 6 plus 1 over 3 is 0, right? And 4 over 6 plus 1 over 3 is equal to 1. Minus 2 over 6 plus 1 over 3 is equal to 0. Oh. Can you see? I'm going to small letter. 1 over 6 minus 1 over 2 plus 1 over 3 is equal to 0. Minus 2 over 6 plus 1 over 3 is 0. 1 over 6 plus 1 over 2 plus 1 over 3 is equal to 1. So it's 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is identity matrix, right? This is amazing result. Can I move on? How about this? Now, lambda 1, lambda 2, lambda 3, so lambda 1 is minus 1, remember? So minus 1, we have 1 over 6, 1 minus 2, 1, 1 minus 2, 1. Lambda 2 was plus 1, and 1 over 2, 1, 0 minus 1, 1, 0 minus 1. Lambda 3 was 2, right? 2 over 3, 1, 1, 1, 1, 1, 1. And let's check what happens. So minus 1 over 6, 1 minus 2, 1, minus 2, 4 minus 2, 1 minus 2, 1, plus 1 half, 1, 0, minus 1, 0, 0, 0, minus 1, 0, 1, 2/3, 1, 1, 1, 1, 1, 1, 1, 1, 1. So let's add them together. So first element, minus 1 over 6 plus 1 half plus 2 over 3. What do you have? 1, right? 6 over 4, 6 over 3 minus 1, that's 1. How about second one? 2 over 6, right? plus 2 over 3 is equal to 1. Minus 1 over 6, minus 1 over 2, 2 over 3, 0. Very good, right? 6 over 4, 6 over 3, 1. Right? And 2 over 6 plus 2 over 3 is equal to 1. Minus 4 over 6 plus 2 over 3, 0. 2 over 6 plus 2 over 3 is again 1. Very interesting. Minus 1 over 6 minus 1 over 2 plus 2 over 3, 0. Right. Good. 2 over 6 plus 2 over 3, 1. Minus 1 over 6 plus 1 half plus 2 over 3, 1. So 1, 1, 0, 1, 0, 1, 0, 1, 1, which is what? A. Isn't it amazing? So when A is an omission, and then you can solve the eigenvalue problem for omission matrix, and it turns out that eigenvalues are real, and normalized eigenvectors are orthonormal vectors, and then they satisfy this spectral theorem. It's a pretty amazing result, isn't it? So if I ask you to can I move on? So A is actually sorry, what am I doing? So A can be written as this. So when A is n by n omission matrix, step 1, solve A lambda lambda. This is eigenvalue problem, right? Then you obtain real lambda 1, lambda 2, lambda n. Normalized lambda 1 vector. Then four more orthonormal vectors, set of orthonormal vectors, then they satisfies identity lambda I is A. So they are spectral theorem. So for example, so actually spectral theorem can be applied by solving the eigenvalue problems for the Hermitian matrix. Then the Hermitian matrix eigenvalues are all real, and the normalized eigenvectors actually form orthonormal vectors set. And then they satisfy the following Hermitian spectral theorem. So for example, am I going a little too fast? Or is okay? Or too slow? Not too slow, not too fast. Just normal pace. So let's go back to 3 by 3, the matrices that we solved. So say A 1 1 0 1 0 1 1 0. Okay, if I ask you to calculate A to the 4, what would you do? Of course, you can multiply this matrix 4 times. It's only 3 by 3, so it's not a big deal. But now you know the spectral theorem. You can have A to the 4 is actually lambda 1 to the 4th, lambda 2 to the 4th, plus lambda 3 to the 4th. We can do this way. So lambda 1 is minus 1, right? So minus 1 to the 4th is just 1. So this is lambda 1, lambda 1. Lambda 2 was 1. So 1 to the 4th is only 1. Again, lambda 2, lambda 2. Lambda 3 is a little bit complicated because lambda 3 is now 2 to the 4 is 16. 2 to the 4. So remember there 1 over 6, 1 minus 2, 1. Do you think I will have enough space? Sorry, I'm going to squeeze a little bit. With a small letter. 1 over 6. 1 minus 2, 1. 1 minus 2, 1. That's 1 over 2, right? 1, 0, minus 1. 1, 0, minus 1. Plus 16 over 3. 1, 1, 1. 1, 1, 1. So 1, 16. 1 minus 2, 1. Minus 2, 4. Minus 2. 1 minus 2, 1. 1 over 2. 1, 0, minus 1. 0, 0, 0. Minus 1, 0, plus 1. Plus 3 over 16. 1, 1, 1, 1, 1, 1, 1, 1, 1. Oh, do we have enough space? Okay, maybe we have to use this space to do some calculation. So 1/6 plus 1/2, 3/16 is 6/1 plus 3 plus 32. So 6/36, right? Is it correct? 1, 3, 32. So this is 6. So first element is 6. Second element minus 2/6 plus 3/16. Six over minus 2 plus 32 is 30 divided by 5, right? Interesting, 5. Third element, one over 6 minus 1/2 plus 16/3. So 6/1 minus 3 plus 32. 5. Oh, interesting. 5, right? This minus 2/6 plus 16/3. 5, right? 5. Interesting. And maybe one more space. 4/6 plus 0 plus 3/16. 32. 36. 6, right? So second element becomes 6. Final, we also need the space here. Minus 2/6 plus 16/3, 42, 5. And 1/6 minus 1/2 plus 16/3 is 5. So there are many 5 and 6. Minus 2/6 plus 16/3, 5. One over 6 plus 1/2 plus 16/3, 6, right? So you can calculate this, I don't know. You can actually multiply 4 times, maybe faster. So this is spectral theorem. So for this case, actually, multiplying 4 times may be take about the same amount of time. But actually, if I ask you to calculate a to the 10, then this will be much faster. So summation matrix satisfies these very nice properties. So eigenvalues are real, and normalized eigenvectors are orthonormal set. And using this eigenvalue and orthonormal set, you can get the spectral theorem. And there are many other properties of Hermitian matrix, and then maybe you can spend some time. So can I move on? Next topic. The matrix is called unitary if dagger is same as inverse. So for example, when A is 0, 1, 1, 0, we have lambda 1 equal to 1. Right. Then the matrix formed by these normalized eigenvectors are actually a unitary matrix. So say set consider the following matrices: 1, 1, 1 minus 1. So this is a new matrix formed from the normalized eigenvectors. And you take the adjoint, what happens? One, 1 minus 1, right? So actually they are the same, but it's also Hermitian. But U adjoint to U is 1/2, 1, 1, 1 minus 1, 1, 1, 1 minus 1. You obtain this, two, you have 2, this and this, you get 0, right? This and this again, you get 0. And finally, you get 2. This is identity. So this is a special case. So actually, U dagger is U inverse. So this is a unitary matrix. And then let's consider 3 by 3 cases and see what happens. Can I move on? So when A is 1, 1, 0, 1, 0, 1, 0, 1, 1, we have a lambda 1 tilde is square root of 6, 0 minus 1, 1, lambda 2, square root of 2, 1, 0, minus 1, square root of 3, square root of 3, 1, 1, 1. So consider this matrix U, lambda 1, lambda 2, lambda 3, square root of 6, minus 2 square root of 6. Very strange matrix. Square root of 2, 0, minus square root of 2, square root of 3, square root of 3, right? The adjoint of U is just column by row, so U dagger is square root of 6, minus 2 square root of 6, square root of 6, and square root of 2, 0, minus square root of 2, square root of 3, square root of 3, square root of 3. So this is not Hermitian, this matrix, right? Because adjoint is different from the original one. But multiply them together. Let's see what happens. Square root of 6 minus 2 over square root of 6, square root of 6, square root of 2, 0, square root of 3, square root of 3, square root of 6, square root of 2, 0, minus square root of 2, square root of 3, okay, the first element, this and this, what do you get? One over 6 plus 4 over 6 plus 1 over 6, you get 1. How about second row, this and this? Zero, right? How about third element, this and this? 0. Interesting, right? How about this? This and this? Again, 0. This and this? 1. And this and this? 0. It's very interesting properties. How about this? This and this? 0. Yeah. Second, this with this, 0. Finally, 1. So, the ego is actually inverse, right? Then we have a very interesting properties. When A is Hermitian, then actually it's a different version of the spectral theorem, but let's say A is Hermitian. D is a diagonal matrix, lambda 1. And U is a matrix formed by the normalized eigenvector, then A can be representing as U, D, U dagger. So there is a representation of extending A becomes U, D, U dagger. So this is a different form of a spectral theorem, sometimes more convenient. And let's just check for 3 by 3. So for previous case, D was minus 1, 0, 0, 0, 1, 0, 0, 0, 2, right? So let's check that. So U was, anybody remembers the form? So U, D, U dagger, square root of 6, minus 2 over square root of 6, square root of 6, right? Square root of 2, 0, minus square root of 2, square root of 3, square root of 3, square root of 3, minus 1, 0, 0, 0, 1, 0, 0, 0, 2. And U dagger is you just change the row by column. So square root of 6 minus 2 over square root of 6, 1 over square root of 6, square root of 2, 0 minus square root of 2, square root of 3, square root of 3. Oh. Just be patient. I'm getting hungry. Actually, I can show it for 2 by 2, which is much easier, but I intentionally do it 3 by 3 to give you more confidence. So let's calculate this first. The first element, if you do this, minus square root, right? And second, this. And second element, this and this gives this and this gives what? Square root of 2, right? And finally, this and this, 2 over square root of 3. And this and this gives 2 over square root of 6. And this gives you 0. And this gives 2 over square root of 3. Finally, minus 1 over square root of 6. Oh. 1 over square root of 2. Finally, 2 over square root of 3, right? Is it minus? Which one? Here? This 2. Oh, minus, right? Yeah, thank you. Otherwise, I could have been in big trouble. And this minus, right? Okay, so let's do it. Well, we need to do only 9 elements, so plenty of time before lunch. So maybe you can give some space. So minus 1 over 6 plus 1 over 2, 2 over 3, what do you get? 1, right? Okay, 1, good. Okay, let's do this. 2 over 6 plus 2 over 3, 1. 1. Let's do this. Minus 1 over 6, minus 1 over 2, 2 over 3, 6 over 4, 4, 0, right? Okay. 3. So 6 more. Maybe we have one more space here. So let's do this and this. So 2 over 6, right? And 0. 2 over 3 is 1. Which space? We need more space. The second. So let's do this and this. So minus plus 2, 2 over 6, minus, no, this and this, right? 2 over 3, or 4, right? Minus 4 over 6 plus 2 over 3 is equal to 0. Good. So we have 0, right? So let's do this. This and this. So I'm going to... Oh. So this 2 over 6, right? Plus 2 over 3. 1. 1, right? Okay, good. The last 3. Start with this. Minus 1 over 6. Minus 1 over 2 plus 2 over 3 gives you 6, 4, 3, 0. 0. Final 2, like a Final Fantasy. Okay, so 2 over 6, right? And 2 over 6, 0, and 2 over 3 gives you 1. 1. Final. You're almost getting there. Minus 1 over 6 plus 1 over 2 plus 2 over 3 is equal to 1. This is the same as what? Hey. Now do you have a face? Can you believe me? My statement? right? So formation matrix actually can be represented in terms of a spectral theorem, but also nicely using this very simple expression, using a U dagger. Then the beauty of this is actually the following. Can I move on to the next page? So now we know that when A is Hermitian, A can be written as U D U dagger. U dagger is U inverse, which is unitary. Then A square is U D U dagger, U D U dagger, right? But the matrix multiplication is associative. U D U dagger U D U dagger, and this becomes identity, right? So it becomes U D square U D dagger. So in some cases, this is much faster. So you can do many times. A to the n is actually U, D to the n, U dagger. So sometimes this is faster than Spectral Theorem. So if I ask to calculate, for example, I can give you A as 1, 1, 0, 1, 0, 1, 0, 1, 1. And I can ask okay, A to the 10. Then simply just multiply this U. Minus 1 to the 10 is 1, right? 1, 1, 2 to the 10. U dagger. You know the form for U, right? U is given by square root of 6 minus square root of 2, square root of 6, square root of 2, 0 minus square root of 2, square root of 3, square root of 3, square root of 3. So in many cases, this may be much faster. Just multiply 3 matrices, and this is diagonal. So and 2 to the 10 is what? 2 to the 10 is 10, 24, right? It's much larger than 1. So this matrix can be approximately this 0, 0, 0, 0, 0, 0. You can actually ignore 1 with 1,000, right? So actually, maybe you can do this way for numerical computation. You can ignore the smaller component. Maybe we can take a break for maybe a few minutes and then continue. I will try to finish the class by 1:30. 네? 벡터 크기를 1로 만들어주는 거야. 그래서 자기 자신하고 예측했을 때 1이 됐어. 람다1, 람다1이 2잖아요. 그거를 앞에 독한 개수 붙여서 자기 자신끼리 분해해서 1이 되도록 만들어. 노멀라이즈.
붙여준 거를.
네. 다른 인덱 스킬이 내적하면 같은 인덱 스킬이 내적하면
이게 그냥 성질이
정이 올수는 네. So we have seen that the Hermitian matrix is very nice. We have several nice properties, right? So Hermitian matrix I'm afraid I forgot to turn off the record, so all the break time has been recorded as well. I guess it says a noise. So Hermitian matrix A has many interesting properties. So eigenvalue problems then the eigenvalues are real. Normalized eigenvectors form an orthonormal set then thirdly the sum of the outer product of normalized eigenvectors are identity if the weighted sum by eigenvalue gives A, it's called the spectral theorem. Fifth, if you form a matrix with normalized eigenvectors, it's unitary, and A can be written as U, D, U dagger. D is simply lambda 1, lambda n. The diagonal matrix composed of eigenvalues. So these are the properties of Hermitian matrix. So this is very nice properties. And then the most important property is the spectral theorem, and probably the last one. So the question is, what if A is not Hermitian? Life would be more difficult, right? So we can ask a question. Can we use similar expansion for non-Hermitian A? So Hermitian matrix is the following properties. So they are, this is the summarize of what we have been doing so far. So say A is a Hermitian matrix, then if we solve the eigenvalue problem for this particular Hermitian matrix, then we found that these eigenvalues are real, and normalized eigenvectors form an orthonormal set. And then if we sum over the output product, it gives identity. And then if we sum with weighted by the eigenvalue, it gives the original matrix, which is called Spectral Theorem. And then you can also form a new matrix with normalized eigenvectors, and we found that this is unitary matrix. And then A can be also written in this way: U, D, U dagger, where D is the diagonal matrix composed of eigenvalues. So Hermitian matrix is so much nice properties, and then so you can calculate, you can define any functions of a Hermitian matrix. But the question is there any similar expansion for non-Hermitian matrix? How about the case of a non-Hermitian matrix? More general case. Answer is yes. Answer, yes. But bit more complicated. So for that, we are going to consider one more property, positive matrix. The matrix A is called positive if and only if for any vector so inner product of A sandwich. So A is applied to the vector V, and then you take the inner product of V is positive. For any vector. Here is for any vector. Any vector. So we can ask a question. Is we can ask a question. Is this matrix positive? Or not? We know one of the eigenvalues is negative. So if we choose the normalized eigenvector for the negative eigenvalue, then this matrix is negative, right? So it's not positive. Not positive because the constraint in the definition of positive matrix is any vector. So we can choose any vector, right? So we can choose not positive because if we choose 3 as then 3a 3 is what? -1, right? So it's not positive. However, actually we need to continue the discussion next week. Just a little bit. On the other hand, we have a new matrix M, A, dagger A. What if M dagger is A dagger A dagger is A dagger A dagger dagger. So this matrix is Hermitian, right? Even if M is not, A is not, so M is always same as Hermitian. How about A free or joint is what? You can write the free A dagger. If it's a transpose of two matrix product, you always change over, right? So free M free A plus A dagger free so say A free is some psi vector, then this is psi, so this is psi, this is always positive. So M is a positive matrix. And Hermitian. So since this is positive, all the eigenvalues are positive. So as a result, we know that so this is Hermitian matrix, so we know that these eigenvalues are real. But since this is positive matrix, we can see that all the eigenvalues are positive. So let quiz is up to here. covers of the positive matrix, but not the polar decomposition. And I'm going to post my class on YouTube today, and also the PDF files on the website, so you can check. So it's a little bit earlier than I promised, but why don't we stop here today? 예?
퀴즈가 누적이라는 거.
퀴즈요? 지난번에 본 범위는 안 봐요. 그 다음부터. 퀴즈는 지난번에 본 범위 다음부터 봐요. 지난번에 너무 지나갔지. 지난번하고 좀 달리. 네.
이거 그냥 귀여운 건가요?
기울. 이거를 새로운 벡터로 하자고 하면은
하면은 이게
이렇게 되니까 이건 항상 0보다 크니까 자기 자신끼리 내적하면 항상 0보다 크잖아요.
시험 관련해서
or positive or non-negative, and lambda 1, lambda n. Then from the spectral theorem we have the following. M can be written as this. The nice thing is we can actually define a square of the matrix. Then square matrix. Because now we know that so using these properties, actually we can expand the arbitrary matrix. So when A is a general matrix, then A can be U root M. U is unitary. And this is called polar decomposition. time, so maybe. I think proof will take a bit longer than 10 minutes, so maybe I'm not going to do the proof of a product decomposition today, but next week. And so that means